morning. And before we proceed, do you have any questions for me from anything up to this level? Any questions? Okay, so if no questions, let's get started with the with what we have been doing. Let me share my screen. So this is where can you guys see it? See the screen?
Yes, sir.
Okay, thank you. All right. So okay, so this basically was the series feedback topology that we talked about. So in here, uh, this what you have here in this blue box is the original transconductance amplifier without feedback, but we are going to provide negative feedback using the output current, because the transconductance output is a current. So therefore you take that and convert that into a voltage, because my input is a voltage, and then I subtract part of I subtract um, something related to the output voltage, output current. So the beta times I naught, beta has a uh, unit which is resistance. So beta times I out is a voltage. So you subtract that voltage from my source voltage, and that is what we are applying into the output, the input of the transconductance amplifier, right? So this whole thing becomes my transconductance amplifier with feedback. Okay, so my new circuit becomes like this. So that this is my input, but this is my output, just like what you had earlier. But now inside you have something more, and now also this circuit is more stable and it has a lower gain, but it has a as other properties that we talked about, right? Likewise, we can talk about the next topology that we are going to talk about, which is the shunt topology, right? Shunt topology is used for trans resistance amplifiers. Okay, so that's number 3. Shunt shunt. So this is for trans resistance amplifier with voltage shunt feedback. With voltage voltage shunt feedback. So voltage is sampled and it is provided as a shunt feedback. Okay, so again let me throw the basic amplifier. Basic amplifier is a trans resistance amplifier, meaning that you convert a current into a voltage because the gain is a resistance, right? So the trans resistance amplifier basically it has an input impedance and output is a voltage source. Okay, that is my trans resistance amplifier without feedback, and I am going to, since this is a voltage, I am going to feed it to a resistor or the load RL. This is a out without feedback. This is my voltage gain. So that gain is a resistance. So we call this trans resistance. So the gain Rm times input current I, where this is my input current I, this is my input impedance. right, without feedback. So this is my amplifier, and my input is a current source. Okay, so I have a current source like that. So I need to connect this to this circuit, but again, now I also have a feedback network. What do we have in the feedback network? Feedback network output is a voltage, so therefore I need to obtain the input to the feedback network. So let me mark this as my this is my circuit, and my feedback network, you need an input which is a voltage, an output which is a current, right? Because it's a input is a current, so you need to convert this into a current. Okay, so this is my output. So this one is the same as the output voltage V out. Okay, so therefore I have to connect it like this. That's my input to the feedback network. This is the feedback network. Okay, and this current has to subtract from the source current. This is my source current IS, right? So IS was going like this initially, but then I need to subtract from it. So therefore, if it was going there, I need to take part of it out of that. So the current feedback should be negative. IS minus IF is the current. So therefore, IF should be in this direction, which is equal to beta times V out. Remember, beta now is a 1 ohms quantity. I equals V over R kind of thing. So beta is the feedback gain. Remember again, I want to emphasize this again. Beta is not the current gain of the transistor. The same notation that we have used beta so far. This is a different beta. Okay, so don't confuse with that. So it's like this. So this is my current. Okay, so this is my new network. So that you see, initially the current was going like that. Part of it now is taken from here. So therefore, what goes into the input of the transconductance amplifier is less than what was there. So you subtract, right? So this is why we call it a negative feedback. Okay, so as you know, if the input is a current, we want the input impedance to be very high, ideally infinity. Uh, I'm sorry, in input impedance to be very low, so that the whole current flows through it, right? Uh, so let's see what happens to the mm, input impedance with this negative feedback connected. Okay, so what we like for a transconductance amplifier is we like low input impedance and we like high and also low output impedance, because output is a voltage source. Okay, so this is what we like to have. So as you can imagine, what feedback does is it reduces the input resistance. Output is not changed because this impedance in the sampling network is infinity, so it doesn't draw any current there. So therefore, output impedance has not changed, whereas the input impedance actually reduces. Feedback reduces the input impedance. It is actually very good, right? So Ri with feedback now will become the initial Ri divided by 1 plus beta Rm. Okay, like that. Okay, so Rm is the original gain. So again, if I do like that, this is my RIF, whereas this is my RI. Okay, so that is the difference. Okay, this is my R out, this is my R out F. Here it has not changed because it's the same as R out, because the feedback network has an infinite impedance. Okay, hope this is clear. Okay, any questions so far? Okay. So what will happen is the, the total input impedance has reduced. Right? So there is a there are two parts. So it's as if you have two parallel combinations here, uh, two parallel resistors, two parallel networks here. Because you have two parallel networks, you'll have a lower resistance, right? We are going to next, after going to these four topologies, we are going to analyze each of these. Okay. Now the fourth network, let me go to the next page, enough space. Fourth one is shunt series. In other words, so this is a current amplifier. You sample the current and feed it back as a current as well. So therefore, feed it back in shunt. So we call this current shunt feedback also. Okay, current amplifier with current shunt feedback. Okay, so what do we have here? Again, you have the current amplifier. Current amplifier has an input impedance and a current source as the output. So this is my original current amplifier. This is the current amplifier. I have input impedance. You have AI times II, right? So the II is this input current, that is the input quantity that we are using, and output is a current like this. Now remember, the direction of current is just a convention. I have taken current coming in and going out so that the gain is a positive constant. If we mark it like in the opposite direction, the gain will be, current gain will be a negative value. So we don't really pay too much attention to that at this point. And you have a load. This is the load. So the same current that passes through this load has to pass through the feedback network, right? So the feedback network, therefore, is a current. So it takes in as a current, right? So current has a current source has a current sampler has its, so you connect it in series. Okay, so you have to have a connection like this. So the same current I out flows through my feedback network, and the output of that is again a current. Okay. So it has to be a current also. So therefore this will be equal to beta times I out, and that is the IF, feedback current. Okay, feedback current in this direction. So that's my feedback network. And I have the source. Source is a current source. We initially started with a current amplifier, so therefore my source is a current source. It has a source current IS. Okay. So initially the current was going into this, and now I have to sample and reduce this current. So again I have to use something like that where the current is reduced. So initially the IS was completely going into the input. Now I am taking part of it into feedback network so that it is subtractive. Okay, so you have this network like that. Okay, so that is my feedback network. So this is the total current amplifier with feedback like that. So my output impedance, you look at the output impedance from here. Okay, this is my output R out with feedback. This is my input impedance with feedback R in with feedback. This was without feedback. Okay, so this is R in, and this was R out initially without feedback. Right? Since again, since there is no resistance in this path, R out F does not change. So R out F should have been R out plus this resistance here, but there is no resistance as such. It is short circuited, so therefore that value will not change. Whereas here, when you are looking at it from this direction, initially you only had this R in the input, but now I have connected another circuit, another network, the feedback network here. It also draws a current, so therefore current is reduced. As you know, now when you have multiple circuits in parallel, the total resistance will be the parallel resistance of these two, the Thevenin's equivalent resistances. They will be in parallel, so therefore the parallel resistance will be smaller than even the smallest the two uh, resistances. So therefore our input will actually reduce. So therefore we can write that down. What we like is for this to have high input, sorry, a high output impedance, because it's a current source. Okay, current amplifier, the output has a current source, and also low input impedance. This is what we like. Okay, so what we have is the output will not change, but the input impedance will be further reduced due to feedback. Okay, so because of the feedback, it will be reduced. So R in with feedback will be equal to R in without feedback, the open loop impedance, divided by 1 plus beta AI. Okay, what is AI? That's this one over here. AI is the gain of the original current amplifier. So that's my um, this is my current amplifier with feedback. Okay, with feedback, it will improve its input impedance as well. Now we have seen the 4 topologies depending on whether you have a voltage amplifier, transconductance amplifier, transresistance amplifier, or a current amplifier. You use different types of sampling networks and feedback or mixing networks. So therefore, uh, we will summarize what we have seen here. Let me say, so when you have voltage feedback, whenever you have voltage feedback, okay. So we had voltage feedback in 2 cases. One is the series shunt case where we had voltage amplifiers, and series where you had um, transconductance amplifiers. Well, basically, whenever you have an input as a voltage, okay, so then only we can apply a voltage feedback signal, right? So in which case we have to subtract this feedback voltage um, from the source, the input signal, right? So we have to series subtract VF. Series subtraction of VF, okay, from the source. So this, because of this, it increases the input impedance. It increases input resistance. Okay, so therefore we saw that whenever we have this, the impedance with feedback becomes Ri divided by 1 plus beta A. A, if it is a voltage amplifier, it will be the AV. If it's a transconductance amplifier, A will be GM. Okay, so depending on the type of amplifier, this A will either have units or not. So we have to basically keep that in mind. Okay, A is equal to AV or GM depending on the amplifier. Okay, whenever you have current feedback, okay, the second one, current feedback, what that means is my input is a current, right? I have a current input, so therefore the feedback has to be the same as the input, so the feedback is also current. Now what that means is I connect it in shunt. I take out part of the current, so therefore shunt subtraction of IF. Feedback current has to be subtracted from IS, the source current, right? This decreases the input impedance. So you have parallel networks. Earlier you had series networks, now you have parallel networks. Decreases the input resistance. Okay, so therefore my RIF will now be equal to RI times sorry, I think I marked it incorrectly in the previous one. This should be multiplied times. Okay, so this should be Ri is this times 1 plus beta A. Okay, because you have to increase it, because b1, so this Ri 1 plus beta A increases. It's great, beta A is always greater than 0, so therefore Ri will be Ri with feedback has to be greater than this. Okay, so this is like that. Okay, so this is the second part is just a comment. The second one, this is where you subtract with by 1 plus beta A. Okay, now hope you guys make this correction. So I have incorrectly marked it as Ri divided by 1 plus beta I, in which case it will be reduced, right? But what we want is increase. This is basically what we had. Okay, so in this case, A can be either Rm or Ai. Okay, I have marked it like okay. Good. So that's basically that. Now, and in the case of voltage sampling, so this is basically the feedback. What will happen to the output? Output will also be duly reduced. We will see this next, but let me summarize it here also as I'm summarizing the effect of feedback. Voltage sampling, that means the output is a voltage. Okay, voltage sampling. In voltage sampling, we are connecting the feedback network in parallel to the output. So therefore, if the feedback network has a finite resistance, input resistance, then it is going to be in parallel with the output impedance. The output impedance has to drop. In the cases that we considered earlier, they had infinite impedance, right? The input impedance of these were either 0 or infinity. In the case of the voltage sampling, it was infinity. Current sampling, it was 0, but may not be the case all the time. Sometimes they have finite impedances. If that is the case, what will happen is, if you put a finite resistance in parallel with the existing output impedance, the output impedance with both these in parallel will be smaller than whatever is the smallest impedance. Okay, so voltage sampling reduces the output impedance, and you will see that this can also be written in this form: without feedback divided by 1 plus beta A. We are going to see whether this is the case, okay, later on. So this is for the, in this case, output has to be a voltage. This is the case for voltage amplifiers and trans resistance amplifiers. So this A can be AV or RM. Similarly, the last one is current sampling. It increases the output resistance. So you can write the output impedance with feedback is equal to R4 times, this is RO, not ROF, sorry, made a mistake there again, times 1 plus beta A. So earlier I have written like this, right? There is no F here. This is output impedance without feedback divided by 1 plus beta A. In this case, the second one, current sampling increases output impedance. So this will be like that, where these can be, A can be either GM or AI. So the transconductance amplifiers and current amplifiers. So that's basically the summary of what feedback is going to do to input impedance and output. Now let's analyze one of the circuits, one of the topologies in more detail, and try to derive these quantities. Okay, that's what we are going to do next. Any questions so far? Okay, all right. So let me go to the analysis then. Let's take the first one, which is the voltage amplifier. So this is a series shunt circuit. Series shunt. So this is a voltage amplifier. Okay, voltage series feedback. So the output is a voltage. You feed it back in series. That's basically what voltage series feedback means. So let me draw the equivalent circuit. rather than drawing everything. What I have is a circuit like this. So you already have the initial circuit. This is the input impedance. All right. This is my output voltage. This is AV times VI. VI. This is VI. Right, so that is my, and then you also have the output impedance R out without feedback. And then I have the output voltage here, V out, and I connect it to the load, R, and this is my output load voltage. Okay, this is my load voltage. The current here is I out. That will be determined by the load. Current will vary depending on the load, and I am going to use the input as a voltage source Vs, and I'm going to connect it. I think I have accidentally stopped sharing. Okay, you guys can see my screen again.
Yes, sir.
Okay, thank you. All right, so we have the input voltage source. So the voltage source is connected here, but now in connecting the source, we have to subtract the feedback voltage. So therefore, I'll mark it as a feedback voltage here. Remember, it has to be in the opposite direction to this, right? So it has to uh, be subtracted from this. So therefore, it should be like that. So that will be my VF. Okay, so rather than drawing all the feedback network, I am going to represent the whole thing in this way, where now my input impedance without feedback is like this, okay, R in. Output impedance without feedback is like this, R out. But with feedback, this is my output input impedance, Ri with feedback, and this is my uh, R out. Well, in fact, R out with feedback would be here, which will be the same with feedback, but R out with feedback and the load, the effect of load, when you connect the load, the effect of load, so that there's a current through it, will be like that. So the ROF dash is with the effect of the load. Let me take that also into account. Okay. So first let's look at input impedance with feedback. Okay, so let me define it. RIF is defined as the ratio of uh, voltage to current. What voltage? The voltage is this voltage. So this is what we are trying to define. So this voltage is what is applied across this. So I assume this is basically a resistor that you have here. The current has to be that. Okay. So Vs divided by Is. Okay. Is will be the same as I. That is the current that flows through my network. This is I input current to the circuit because it is in series. Okay. So therefore, this I can write as Vs divided by I But what is Vs? Vs is equal to this voltage plus this voltage equals this voltage, right? So therefore Vs is equal to the I1 IIRI, that's the voltage across this resistor, and I have to add Vf into that, right? Vf. But we know Vf is equal to beta times V out. Okay, so therefore IIRI plus beta times V out. That's my Vs. I can write it like that. What I'm trying to do is get the expression for this and that. Okay, so that I can find an expression of RIF. Now V out we don't know, so we need to write that in terms of something else. So therefore, let me try to eliminate V out. So the V out I can write as this is the output voltage. So this should be the voltage here minus any voltage across this. Okay, so that will be AV times II. So that's so AV times AV times VI. I'm sorry, AV times VI times. Now I can look at it as a voltage division. So this is the only voltage source that I have, and that voltage, the output voltage V out, so this is the V out here, will be the voltage division between this resistor and this resistor. Okay, so therefore I'm going to write V out as a RL divided by RL plus R out. Okay, hope this is clear. Right, so this is basically I have this voltage applied across these two resistors. The current is the same that is flowing through these two resistors, so therefore there is a voltage division that I can look into. So V out can be written as V out is equal to RL over RL plus R out times this voltage here. Okay, so that's this. So let me call this the what is VI? VI is this voltage across this resistor. VI is equal to II times RI. Okay, VI is basically VI is equal to II times RI. Okay, so for this resistor, okay, that resistor it will be like that. So therefore, I can write this as AV times RL over RL plus R out times VAV times this quantity times VI. VI is II VI. Sorry, II RI. Okay, so from here, let me call this whole quantity AV dash times IIRI, where AV dash is defined as V out over VI with the load. Okay, with the load, which is equal to AV RL over RL plus R out. That's the definition of AV dash. AV dash is nothing but the voltage gain without feedback, but when loaded. When it is loaded, this is the when the load is connected, and there is a current through it. Right. So therefore, I can now I have an expression for V out, which I can put here, which can be written in terms of IIRI, and therefore there's another IIRI here. So therefore I can completely replace this Vs in terms of II. Okay, so that I can get an expression like that. Okay, So therefore I can write therefore RIF, which is equal to VS over II. VS from this I can write is equal to IIRI plus VF, which is beta times V out. So the beta times V out. What is V out? V out is equal to, from this expression I can write AV dash RI I, okay, divided by this II here, so that this simplifies to Ri times 1 plus beta AV dash. Okay, this is basically what you will end up with. And if you want, you can further, replace AV dash with a RL over RL plus R out. Okay, so this is basically the expression that you have for the input impedance with feedback when it is loaded. Okay, so yeah, AV is the open circuit voltage gain. Without feedback. AV dash is the voltage gain, open circuit again, without feedback when loaded, when the load is connected, when loaded, when the output resistor is connected. Right? So if you remove the load, what will happen is AV is basically limit of RL goes to infinity of AV dash. So AV dash will approach the value of open loop gain when output is not connected. Okay, so when the load is very load resistor is very large, so the load is small. Okay, current is very small, so when RL is much bigger than R naught. Okay, so according to this expression here, RL is much bigger than R out, so then therefore RL over RL plus R out, everything divided by RL, right? So this is 1, this is 1. R O divided by RL will be very small because R out is much smaller than this, so this will be approaching 0. So this whole thing will be roughly equal to 1. So therefore I can write AV dash approaches AV. Right? So the important thing to remember here is the input impedance. We have proved that input impedance Ri with feedback is equal to Ri 1 plus beta AV. AV when there is no loading, there is no RL connected. The RL is infinity. This is basically what we have used earlier. Okay. So as long as we have voltage as the feedback, in other words, the input is a voltage, we can always use this expression because the input circuit will not change. Whether the output will change, but this will always be the same as long as you have a voltage input. So therefore, this will be the same for same expression for uh, transconductance amplifier as well. Okay, let me write that also. As long as we have voltage Vf as the feedback, Ri with feedback will be equal to Ri 1 plus beta A. Okay? A is equal to AVOGM. That's basically something that we uh, wrote in the previous page. Then this is the uh, derivation of it. Okay? So you see it is not difficult to derive that. Now we did not derive an expression for the voltage gain. So let's see how to do that. Closed loop voltage gain. Voltage gain. Let's assume RL is much bigger than R out. In other words, the effects of loading is not taken into consideration. Okay, all right. So a closed loop is equal to, is defined as V out divided by Vs. So the whole output divided by the whole input. Okay, so the ratio between this and that. Okay, the output and input is the closed loop gain. But V out, we know, if you don't have the loading, is equal to AV times VI, because there is no voltage drop across the R out, because I out is equal to 0 when the load is infinity. Okay, so that's why we can write it like that. This is divided by Vs. We already obtained an equation for this. Vs is equal to the Ri plus Vf. These two, this expression Vs is that. So we already obtained an expression for this. We can write it as Vi times beta V out, which is equal to A V Vi divided by Vi plus beta V out is AV times Vi, which is equal to AV 1 over 1 plus beta AV. Okay. So we have the expression for the closed loop gain, where uh, Vs is equal to Vi 1 plus beta AV. Okay, that we have proved earlier, and V out is equal to the closed loop gain times Vs, which is equal to AV 1 plus beta AV, that is my closed loop gain, times Vs. Okay, so that's my expression. So let me highlight the important thing. ACL is equal to AV over 1 plus beta A. So that's the second thing that we derived. Okay, so let's look at the output impedance also similarly with feedback. Output impedance. Now you have, let me draw this diagram again. So you have the Vs, and then you have the input impedance without feedback. This is Ri, and then you also have the feedback signal, right, like that. This is beta V out, and you have the output voltage gain AV times VI, AV times VI, and then you have the resistance R out, and then uh, you have the output voltage V out. Okay. Now here we define R out with feedback, we R out F, as when you have V. So this is the definition, when Vs is equal to 0. Then in other words, we are going to short circuit this input circuit, and we are going to define this as the V out divided by I out. Remember, this is exactly what we did for the transistor also. We defined the output impedance as the ratio between output voltage and output current when the input is short circuited. Remember, then we came to the issue of, if there is no input voltage, there will be no output voltage, so there will be no current. So how do you find it? But remember, then what we did to overcome this was to connect a source from the output and measure the voltage. So we can either connect the voltage and measure the current, or we can connect the current source and measure the voltage, or connect the voltage source and measure um, the current, right? So in this case, what we are going to do is we are going to connect a voltage source, and that value we know is the V out, and then we are going to measure the current. Okay, so we are going to measure the current I out, we are going to measure it, and that is the ratio of that. Okay, so this is basically these two are basically obtained from that. Okay, you can do it either way, by connecting a current source and getting it also. And remember, there is feedback, here, but remember, since it is a voltage feedback, if this feedback network has infinite infinity, there is nothing dropping around this. Okay, there is no current flow, but anyways, we can write it that like that. So with V, this is the definition. Okay, Vs is equal to 0. So this is the definition. So we output, so this, let me code it like that. Right, so I out is equal to V out, which is a voltage source now, minus the voltage here, AV times VI, I, divided by the resistance in the circuit, which is R out. Okay, but we know VI plus beta V out by applying the Kirchhoff's voltage law to this circuit is equal to Vs, but we have made Vs equal to 0 by definition. Okay, so this is equal to 0. So therefore, Vi is equal to minus beta V out. So therefore, what do we have as the I out in this expression? I out is equal to V out minus AV times beta V out, from this, Vi is that, divided by R out. Okay, so I can now write R out with feedback is equal to V out over I out. So from here, I can take R out here and take this part to the denominator, and we will have 1 yeah, see, I have forgotten this negative sign, so there you have to have the negative sign, negative, negative, so this will be positive, right? So Vi is negative here, Vi is negative, that negative times this negative will be positive, so therefore 1 plus beta AV. Okay, So that is how you have the output R out with feedback is equal to R out divided by 1 plus beta AV. Okay, so this is how output is reduced for the voltage amplifier. Now, if you load it, if the output is not equal to infinity, okay, the load is not infinity, with load with load with load as part of the amplifier, ROF dash, this will be equal to, if you have this as the ROF, you just have to parallelly connect the R load. This will be how you will get this one. Okay, so that's basically as simple as that. So this is basically this shows you the input impedance. Now remember, the reason why we use this was, this is a definition. This is the definition of the output impedance. Sorry. Okay. So this, because of that output impedance. So even if you don't have a resistance here, you see that output impedance has actually reduced, even when there is infinite uh, impedance there. Okay. So you see the output impedance has reduced for voltage amplifiers, and also the output circuit will be the same for the transconductance amplifier, um, trans resistance amplifier. So therefore for that also, and also for trans resistance amplifier. So whenever you have an output as a voltage as an output, the output impedance reduces. Okay, so this is basically, we are going to stop today's lecture. Do you have any questions from this section? Any questions, guys? No questions? All right, if you don't have any questions, we'll continue on this section from Monday. So we'll take an example and see how to actually apply these principles to solve um, a practical circuit, right? For example, um, a voltage series feedback or series shunt feedback, we'll see that we have already seen some circuits like that. That is basically the common collector circuit with feedback, common emitter, common collector circuit is actually a voltage series feedback circuit. And how do we analyze that? Okay, so let's have a look at it next week on Monday, and we'll go from there. Okay, we'll stop our class here. Thank you.
Thank you, sir.